All right. So we're going to be looking at working with imaginary numbers and complex numbers. So to begin, we should go ahead and define what we call the imaginary unit. And this, which we denote with an I, is by definition the square root of -1. Um, Basically, mathematicians ran into the situation where they wanted to be able to square numbers and get negatives. And so they said, well, to solve certain problems. I mean, they just didn't want to do it, just do it, but to solve certain problems. And so they came up with this new notation, I equals the square root of -1. So now that we can simplify things like the square root of -12 by thinking of that as square root of 4 times the square root of 3 times the square root of -1. So 4 times 3 times -1 is -12. Square root of 4 is 2. Square root of 3 doesn't break down, square root of 3. And by definition, the square root of -1 is I. Now, some people, they prefer to write that as 2I square root of 3. I don't like to write it that way. You'll see in a second why. But if you choose to, that's okay. That's fine. It's still correct. What you don't want to do is something like 2, and notice how I'm putting the I under the root. That would be bad. Don't do that. So if you find you're doing that, then put the I in the front and keep yourself from making that mistake. But the I should not be under the root when you're writing things this way. Okay, so looking at this I, one of the things we might want to know is what happens when we start multiplying these things together. And so we're going to look at the powers of I to the first power, that's just an I to the second power. Well, remember, by definition, I is the square root of -1. So if you square that, the square and the square root cancel each other out, and you're going to get what's inside. So I squared is -1. So like I said, this allows you to square a number and get a negative with these i's in there. I to the third, well, that's 2 i's times another I. -1 times I is -I. I to the fourth, well, that's 2 i's times 2 more i's, so -1 times -1 is +1. I to the fifth, well, that's 4 i's times 1 more I, so 1 times I is I. I to the sixth, well, that's 4 i's times 2 i's, 1 times -1 is -1. I to the seventh, well, that's 4 i's times 3 i's, so 1 times -I, -I. I to the eighth, well, that's 4 i's times 4 more i's, so 1 times 1 is 1. And what we see is it goes through this cycle of every time I hit a multiple of 4, then we wonder, we start the cycle over again. So you hit 1, and then the cycle starts over. And so if I wanted to know what is I to the 347th power, what I would ask myself is, how many past a multiple of 4 is this? And I believe 344 is a multiple of 4. So this is 3 past that. So this is equivalent to I to the third. I to the third is -I. So you're always going to get one of these 4. And half the time it's going to be real numbers. Half the time it's going to be imaginary numbers. There's always going to be one of those 4. So if you're ever going to have a problem and you have like an I squared at the end of the problem, you're not done with the problem. You need to go further. With the negatives, it gets a little bit more complicated. Basically, you just want to keep adding multiples of 4 until you get it up in the positives to figure out what it's equivalent to. That's the easiest way to do that. All right, so this brings us to probably the biggest set of numbers we're ever going to run into, and that is the complex numbers. And the complex numbers have the following kind of definition in set form. They look something like this. A plus bi such that this A number and this B number are elements, that's what this means, elements of the real numbers. So you got a real number plus a real number I, that's a complex number. So if we have 8 minus 4, or 8 plus 4i, that's a complex number. If 8's a real number, 4 is a real number, complex number. If you have 6 minus 5i, that's a complex number. 6 is a real number, and when we say minus 5i, what we really mean is this is plus negative 5i. So that just means the 5 is negative. So, you could say plus or minus here. That just means if it's minus, that just means the b value is a negative. You can even have things like the square root of 3 plus pi I. Square root of 3 is a real number, pi is a real number. They're just not rational, but they are real. They're irrational numbers. So this fits that pattern. You can even have things like 2 minus the square root of 3 plus 4 plus the square root of 2i. So all of this would be your a, all of this would be your b, I. And that still would fit that pattern. So if you ever run into a situation where you're trying to add numbers together and they're not like terms, you have rational numbers and irrational numbers and you can't put them together, what you do is you group them together, group all your real numbers and all your imaginary numbers together, factor out the I, your imaginary numbers. So this A is called the real part, and this BI, this is called the imaginary part of the number. Okay, so 8i fits that pattern because this is really 0 plus 8i. So anytime you have a pure imaginary number, that's just a complex number, but the real part is 0. And then you get into, the kind of mind-blowing things that, like 25 is a complex number because that's really 25 plus 0i. Again, it just means the imaginary part is 0. So every real number is a complex number where the imaginary part is 0. So every number we pretty much have ever seen is a complex number, which is good because we know some things about working with certain types of complex numbers, and it's going to help us to work with, get insights into working with all complex numbers. So let's say we want to add or subtract some complex numbers. So, things might already be kind of set up for us. Say I want to add these two complex numbers together. What I want to do is combine like terms. So notice these parentheses, this is just saying this is a complex, this number, but they're not doing anything mathematically, they're not multiplying or anything because it's adding in between here. So what I'm going to do is I'm going to rearrange this 3 plus 5, 4i minus 6i, and then, just combine like terms, 8, 4 minus 6 minus 2i, and again, that's just plus negative 2i. I don't write it that way, but, we all know that just means the 2 is negative. But a lot of times, this will require you to do a little bit of work. Say negative 45 minus 11 plus negative 20. And so what do we got? 5 minus, and I'm going to ask myself, what times what, gives me this? Well, 9 times 5 times negative 1 is going to be a 3 root 5i. And then I'm going to distribute this negative through here. So negative 11 minus, and again, what makes square root of negative 20? 4, 5, negative 1, so 2 square root of 5i. Put the things that match together, 5 minus 11. Put the other parts together, 3 minus 5 square root of I minus 2 square root of 5i. Combine like terms, 5 minus 11 is negative 6. Negative 3 root 5i, negative 2 root 5i is negative 5 root 5i. Remember, when you're adding or subtracting things with roots attached, you just combine, as long as the root parts match, you combine the coefficient part, the number part in front, and there you go. There it is. And again, make sure that I doesn't get under that radical. It stays out of there. All right, multiplying. Multiplying here, there is one little trick to multiplying roots, and that is you gotta, we say, take the i's out first, right? And what we mean by that is, let's say, we'll take a kind of a real simple example. Let's say we have square root of negative 5 times the square root of negative 20, okay? And if I were to just multiply these together, as is. So the way you multiply root statements is you multiply outside parts, so 1 times 1 is 1. You multiply inside parts, typically. -5 times -20. So a -5 and -20 make a positive 100. You get 10. You know, that doesn't actually give you the right answer. That's the wrong way to do the problem. Instead, what we need to do is we say, oh, there's a negative in here. That means there's an I. There's an I here. And there's a negative here. That means there's an I. So we need to make those I's appear. That's what we mean by take the I's out. Take them out of the root and make them appear, then multiply. So what we're going to do is, again, outside parts, inside parts, you know, match up. So 5 times 20 is 100, square root of 100. I times I is I squared. Square root of 100 is 10. I squared is -1. 10 times -1 is -10. That's the correct answer. So not this. This didn't work. That's the kind of big trick. Now, a lot of times what you'll get is something like 5 minus 4i times 6 plus 7i. And what are we going to do here? We're going to FOIL. We're just going to distribute this out. So like we would a polynomial. So 30 plus 35i, negative 24i, negative 28i squared. And then you're going to say, well, I squared is really, that's a -1. So -1 times negative 28, that's a positive 28. All right. So positive 28, positive 30, 58, 35i minus 24i, and it looks like 11i. And there we go. There's our answer. Again, how do I know when I'm done? Either you're going to get something like a plus a number I, a minus a number I, and that just means the number is negative. Or you might just get a real number. You know, like we got -10. That's just a real number. Or you might just get an imaginary number, like 5i or something. You know, that would also be. So one of these, if it doesn't look like one of these four at the end, then you're not done yet. And you need to still work. Like I knew this wasn't going to be done until I got rid of that I squared to finish working out. Okay. By the way, I never really explained why I like to write the I in the back. Like in this case, why do I write the I here? Well, the reason why I would prefer to write this the way I did here, instead of writing it as, say, this, is if I said, well, what's A? You know, remember we said this, we want this to be A plus BI. And then what's A? Well, A is -6. That's pretty clear in both ways. But if I said, okay, what's the B here? Well, if you look at how I wrote it, it's whatever's in front of the I. So it's all this, -5 root 5. But if you write it this way and ask what's the B, well, some of it's here and some of it's there. Your B's kind of split in half there. And that's why I don't like to write it that way. It kind of separates the B up. Instead of saying it's -5 root 5, that's a number. Five times as big, you know, -5 times as big as root 5 is. It splits it up. So that's why I don't like to do it. But like I said, it's fine. You can do it that way. Just keep in mind all of that is B. Okay, so let's go to dividing. And dividing is probably the trickiest thing we're working with here. Okay, so remember, I by definition is the square root of -1. That means when we're talking about dividing, we're talking about dividing by roots. So let's kind of remind ourselves here. Reminder, right? If you have like 5 over root 3, well, we don't like to have a root in the denominator. It's called rationalizing the denominator. We don't like that root down there. So what we're going to do is we're going to multiply by something that will make the bottom a perfect root. And so I'm going to multiply by square root of 3, and that's going to give me 5 over the square root of 5 square root of 3 over the square root of 9. Square root of 9 is 3. So no more root on the bottom. Now it's okay to have roots on the top, but it's not okay to have roots on the bottom. So you can think of something similar, like, you know, simplify 5 over 3i. I don't want an I in the bottom. And so what I'm going to do is I'm going to multiply top and bottom by I. And the reason why I'm going to do that That's going to give me I squared on the bottom, and I squared by definition is -1. So 3 times -1 is -3. And then what I'm going to do is I'm going to kind of, remember I want to say what is A, what's B, I want to figure out what that is. I'm going to kick that I off the side and write that says -5/3 I. Think about slope. If you're wondering, why can I do that? Well, remember you do that with slope all the time. So that's all we're doing here. Is in this case, the A is 0. We don't have a real part, but the B is -5/3. Okay. Now, remember when we're dealing with particularly square roots, if you have something like this, we couldn't fix this by just multiplying by √2. If I did that, all it would do is it would make this part a nice, perfect thing that'll break down, but then I have to multiply this by a √2, and I still have a √2 on the bottom. It doesn't make it any better. So what we had to do is do it a little bit less directly. We have to multiply this by 4 plus √2. Not the opposite, but what we call the conjugate. This is the conjugate. And what we're setting up here is A minus B times A plus B, A squared minus B squared, the difference of squares. That's what we're doing. So what you're going to have is you'll have half of the difference of squares, and you'll have to get the other half. So if you start with a plus, you're going to multiply by a minus. Start with a minus, you multiply by a plus. But one of each is what you need. And then you're just going to multiply. Let's see, distribute. That's 12 plus 3√2. Multiply out. Again, this is going to be the difference of squares, so it's going to be 16 minus the square root of 4, which is 2. So 12 plus 3√2 over 14. And now you could leave it that way, or if you wanted to, you could write this as 12 over 14 plus 3 over √2 over 14, and then say that's 6/7 plus 3√2 over 14. Remember, these don't cancel each other out because the 2's under the root and the 14 is not, so they don't cancel each other out. I don't know why you'd want to do that exactly, but you could. You have that option. Now, when we deal with complex numbers, and we kind of run in the same situations, let's say we have 3 minus 2i over 5 plus I. What I'm going to do is I'm going to multiply by 5 minus I. Again, it's all about the bottom. It's all about rationalizing the bottom, making the bottom come out to be a nice number. So again, it's the difference of squares is what we're setting up here. We call this, whenever you just change the sign of the imaginary part, you call that the complex conjugate. Because we're dealing with complex numbers, right? So complex conjugate. So we're going to multiply all that out. So a little bit more, let's see, 15. Again, I'm just foiling. Minus 3i, -2, 5, and -10i. -2i is positive 2i squared over, again, this is just the difference of squares, so 25 minus I squared. And then we go, oh wait, I squared is really -1. So this is -1 times 2 is -2. -1 times a negative, that's going to be really a +1. So combining like terms, 15 minus 2 is 13. 30, okay, minus 13. Well, that's kind of unusual, but whatever. Over 26. Now, I said in the previous one we could split it up or not. In this one, we have to. I have to split this up into 2 fractions. Now, the reason why I have to do that is because I need to know who's A and who's B. And if I leave it as 1 fraction, it's not clear who's A, who's B. So I got split up into 2 fractions, who's A, who's B. And luckily here, these actually do reduce. 26 is twice 13, so this is going to be a half minus a half I. It just came out. We got lucky that way. It worked out that way. But I do need to split up. So I can say, oh, that's A, and that's B, and that's I. So I have to split it into 2 separate pieces, 2 separate fractions. All right. A couple other things here related to here. What this means now is now we can solve any quadratic. Let's say I had 3x squared minus 5x plus 7 equals 0. So I want to solve that. And it doesn't factor, but it is a quadratic, so I can use the quadratic formula. X equals negative b, negative plus or 5, okay, b squared minus 4 times a times c all over 2 times a. All right? So what are we getting here? We got 5 plus or minus, we got 25, we got a 6 down there. What's this? 21 times 4, negative 84. Looks like square root of negative 59. So x equals 5, 6 plus or minus the square root of 59, 6, I. And we got two answers. So now that we get a negative under the root, that's okay. You can get negatives under roots. That doesn't mean you stop. You just keep working. You just now get an I term. And just remember that these are two separate. This is A, this is B, two separate things. So we can now solve every quadratic equation, every single one. All right. Last thing with this complex numbers is we want to look at the complex plane. All right, so you can think of every real number you can think of is somewhere on a number line, right? 1, 2, 3, 4. So pi is like 3.1, something is around there somewhere. Square root of 2 is 1.4, something is around there somewhere. So every real number is somewhere on that number line. And you could look at relationships between different real numbers. But with complex numbers, you can't just use a number line to describe where they are and see like some relationships. So what we use instead is we use a plane. We use that was badly drawn. Okay. Not as easy as it looks, guys. Okay, let's start here. Oh my gosh, this is horrible. Yeah. I cannot draw a straight line to save my life here. Okay, anyway, I, 2i, 3i, negative I, negative 2i, negative 3i. You get the idea. Okay, so we use a plane where the vertical axis is the imaginary numbers. And so if I say, okay, I want to know where is 3 minus 2i at? Well, it's 3 in the real direction, and it's a negative 2 in the imaginary direction. That's why it's very important you can figure out what A and B are. Where are they? This is 3 minus 2i. That's where it is in the complex planes. And there's all kinds of things this is related to in higher level mathematics. We're not going to get into all of that. You can talk about roots of numbers here. What if I wanted to take the square root of 3 minus 2i, and there's ways you can do it. But we're not going to get into all that. One thing we can do in this course with this is I can say, let's find the absolute value of 3 minus 2i. Okay? And if you're thinking 3 plus 2i, no, that's not the absolute value. Absolute value doesn't make things positive. I know that's what it seems like. A lot of times that's not what it does. Instead, what absolute value is, it asks you how big is the number, how far is it from 0? How far is this dot from the 0 plus 0i spot, the origin? Well, let's see, what do we know? We know it's going to be hard. We'll see how this works. 3 units this way, and we know it's 2 units this way. And the question is, well, how far is it, diagonally? What's this? Well, again, if my drawing skills were a little bit better here, what we'd see is this is a right triangle, and we know something about the sides of a right triangle. a squared plus b squared equals c squared, the Pythagorean theorem. So 3 squared plus 2 squared equals c squared. 9 plus 4, 13 equals c squared. Well, what is 3 minus 2i, the absolute value of 3 minus 2i? It's the square root of 13. And again, it's positive. You know, normally if I'd solve a problem like this, I'd say plus or minus, but since we're talking about a distance, it's positive. So it's got to be positive square root of 13. So absolute value always still comes out to be a positive number. So that's something we can do. We can plot complex numbers in the complex planes, and we can find their absolute values. So, all right, that's our introduction to complex numbers. We're going to work a little bit with complex numbers in the next